Okay, so hello everyone. My name is Maïmouna Brigitte, and I'm a PhD student with the Elis Swoboda in the Astronomical Institute of the Czech Academy of Sciences in Czech Republic, so in Prague. And so today I'm going to present the multi-wavelength monitoring of the high mass X-ray binary Cygnus X-1. So this project is in collaboration with people in the Astronomical Institute in Czech Republic, but also from abroad, from the UK, the US, and other institutes. So first, I'm going to present to you Cygnus X-1, which is, as I said before, a high mass X-ray binary. Then I'm going to present the observations that we performed with optical telescopes, the analysis of these results, the results, and the conclusion. You can hear me properly, right?
Sure, no problem.
Yes. Okay. So Cygnus X-1 is one of the first X-ray binaries that was observed in like the 60s. So we have a lot of observations and data in different energy ranges. So in radio, optical, X-rays, gamma rays. And so because of the very wide covering that we have, we were managed to actually have very good constraints on the parameters of the system. So we know that the system is a high matrix binary at around 2 kiloparsec from us, with an orbital period around 5.6 days, an inclination around 27 degrees. And the system is composed of a star, a massive star. Can you also see my cursor
Sure.
moving? Yes. Okay, so this one is the massive star, which has a mass around 40 solar masses and an effective temperature around 31,000 Kelvin. And the star is orbiting around the black hole. And the black hole has what we call an accretion disk, which is the matter falling into the black hole and it's spiraling around because of the conservation of the angular momentum. And the black hole is believed to be around 21 solar masses, which is one of the highest masses we can have for X-ray binaries, and to have a very high spin between 0.8 and 0.9. And so the accretion disk is structured with what we call a corona, which is a very highly comptonized medium, which is usually situated in the inner region of the accretion disk. And the system also ejects relativistic jets along the rotational axis of the black hole, which is mainly emitting in radio. So this is mainly because of the synchrotron emission. And the system, oops. Yes. So the system is known to emit in X-rays. So that's why we call them X-ray binaries, because they are super bright in X-rays. But in X-rays, you usually probe the region closer to the black hole. So X-ray binaries are known to be highly variable in X-rays. So they go from what we call a soft state on the left, where we are dominated by the emission from the terminal black body emission from the accretion disk. So mainly the soft photons are emitting from the thermal emission of the accretion disk, and we can see that in the spectra. So on the bottom, you can see the spectrum for Cygnus X-1. So on the left is the flux, and on the x-axis is the energy. And the soft emission from the soft state dominates between 1 and like 5 keV, so a very soft energy range. And then the system will transition from a soft state to a hard state. In the hard state, there is kind of this very strong corona, which is dominating the spectrum. So it becomes uh, dominated by a parallel emission at higher energy, so above 10 keV. And so the soft emission is completely dimmed because of the presence of the corona in the inner regions. But the particularity of Cygnus X-1 is that it never completely transitioned to a soft state. So technically, we still have a very weak corona, which is still present, which means that we have some of the comptonized emission at high energy still present in the spectra. And here I'm going to present the results that we had in both of these states. So in the hard state, we had observation in 2022, which we call the low X-ray flux, actually, because we have a lower X-ray flux than in the soft state. And then in the soft state, the source was in the soft state in 2023, so we managed to have observations in both states. So now I'm going to switch to optical. And in optical, we are dominated by the emission from the star, so the massive star. So we kind of completely forget what's happening closer to the accretion disk. So the first question that we actually wanted to answer with analyzing Cygnus X-1 was how do the X-rays can actually be correlated with the optical? So basically, how does the accretion disk emission is correlated with the emission from the star? And this question has been asked already in the 2000, beginning of 2000, but we lacked a lot of observations. So we did a lot of simulations were actually done in the two different states that I defined before, so in the hard state and in the soft state. And for example, here in the low hard state, Shikura and Hadalava in 2015 simulated the emission from the accretion disk and from the star, and also estimated the density of both of the components for different states. So on the right, you can see in the low hard state, and here it's in the highest state. So if I go back to the low hard state, we can actually see that the density of the accretion disk is very high, and we also have the velocity of the material which will be accreted from the star toward the accretion disk, which is also very high. So you can see it in the middle panel because the velocities are, the blue is very low and the red is very high. So you can see that the red is actually higher on the outer edges, the opposite side of the black hole. And then we can also have an estimate of the ionization near the black hole. And again, the dark blue is very low and the yellowish is very high. And so when we are, for example, in the soft state, if I keep switching between the two, you can see that, for example, on the first panel, the density is higher in the low hard state than in the soft state, which means that the X-ray emission from the accretion disk has a direct impact on the density of the accretion disk around the black hole. And then if we also look at the velocity here of the outflowing emission from the disk and from the star, the velocity is very low in the highest state, already in the middle panel. Whereas in the lower state, the density is actually higher. And for the ionization is higher in the lower state rather than in the highest state. So these were kind of predictions from the simulations. But now when we compare with observations, we had to perform observations in, as I mentioned before, in the two different states, so in the lower state and the highest state. And to do so, we needed optical and X-rays observation because optical will probe what's happening closer to the star and X-rays will probe what's happening closer to the accretion disk. So with optical, we performed observations in 2022 when the source was in the lower state, and then in 2023 when it transitioned from the lower state to the highest state. And we did that with the Andreev 2-meter periodic telescope, so in Andreev in Czech Republic. And we had in total 67 spectra. And the particularity of the 2-meter periodic telescope is that we have two spectrographs, the CCD 700 and the Escher spectrograph. And what we mainly use for the analysis here is the Escher spectrograph because it has a very good power resolution in the H-alpha region, around 40,000. So with this, we are actually able to separate the different emission and absorption lines from the spectra and to analyze them. But the CD700 has a lower resolution, around 24 or 12,000, depending on the length of the order in the spectral diffraction orders. But what is important here is that we use the Escher spectrograph for the analysis and the CCD700 for the calibration because it has a wide interval of wavelength. So we can have a wider wavelength range around the H-alpha region, which is very broad. So it's very important to have this coverage as well to calibrate correctly the lines in the spectra. So if I show you, for example, the spectra that we had for the hard state on the left and the soft state on the right. So this is around the hydrogen helium region, around 4,000 angstrom. And so these spectra are for the Escher spectrograph, so the ones with a very good spectral resolution. And what we can see on the left are the identified hydrogen and helium lines. And if you compare them with on the right, for example, if we focus on the H gamma line, you can see that the line is broader in the hard state here than in the soft state here. And that is kind of introduction to what we expect to see in the hard state and in the soft state. So how much the stellar wind is actually influenced by the different X-ray spectral states. And now when we have a look at the most obvious line, which is the H alpha line at 65 and 62 angstrom, we can see here on the left that in the hard state, the line is very peak, like has a very high peak and broad peak. And then in the soft state, the line completely collapses, which is again a direct consequence of how the X-rays can actually influence the shape of the lines in optical, so directly related to the correlation between the wind and the accretion disk emission. And now that we have the spectra, we need to analyze them. And to do so, we use the Fourier disentangling method, which was a method first introduced in the 90s. And this method was previously used for binary systems where we only had two stars, and we wanted to separate the emission of each of the stars, especially when they were eclipsing, because when we eclipse, we don't really know which line is emitting in which spectral region. So it was kind of hard to separate the emission from both of the stars where their spectrum was kind of entangled. But in this case, we use the method on the same system, within the same system, and we want to separate the emission from the stellar atmosphere, so closer to the star here, and what we call the focused wind. So the focused wind is kind of this clumpy wind, which is being accreted by the black hole. And the wind is going to travel from the stellar atmosphere towards the black hole. And when it's going to be traveling in between, that's where we want to isolate the emission from this wind, the focused wind. So the Fourier disentangling method here is basically, so we combine the different Doppler shifted spectra that we had in optical. So here is the example that we had in the soft state. So we have the method separate in the hard state and in the soft state. So we combine the spectra in the two different states. And the purpose here is to combine the Doppler shifted spectra and then to isolate the spectral signature of the photospheric region, the focused wind, and the atmospheric lines, which are basically just coming from the Earth. So the atmospheric lines are not intrinsic to the system, but what we will be focusing here is on the photospheric region and the focused wind region. So with equations, basically, we first have the hypothesis that we are in a non-relativistic regime, which is the case because our wind is not propagating at the velocity of light. We also need more spectra than the number of components we need to separate. So for example, in this case, we have two regions that we need to separate. So we need to have more than two spectra, which actually the more the number of spectra, the more accurate is the disentangling. And then we need to isolate the intrinsic observed spectrum, which is the J here. And this intrinsic observed spectrum is actually very important, and we need to make the assumption that it's not too much variable in time, because otherwise we cannot isolate the intrinsic observed spectrum, which is supposed to not be variable too much, because otherwise we cannot separate it from the orbital motion of the system. And in the case of Cygnus X-1, this assumption was not that straightforward because the system is very variable. But because we really selected regions when the system was in the hard state and in the soft state, this assumption was fulfilled because in these states, the system is not as variable that it would be in between systems. So once we have this quantity, we want to actually isolate the total intensity, which is X, T, and P. And we want to determine the orbital parameters of the system, so the P factor, and also the other parameters, which are the instantaneous radial velocity, which also depend on the orbital parameters. And the other important parameter is the strength factor, S, which determines the intensity of the lines with respect to time. And so once we have this, so we can decompose the total intensity into a sum of intrinsic spectra with the strength factors and radial velocities because they are Doppler shifted. We can apply the Fourier transform to get rid of the convolution product here. And then we have kind of a simple least square fit method maximization in which we just need this to be minimal, to be able to actually have the intrinsic intensity of each of the different components. So once we apply this in the different states, we were able to focus on different regions of the spectra. And first, we focus on the H alpha region because it's kind of the obvious one to look for when you're looking at the wind. And so the top panel represents the different observed spectra that we combined together to separate the emission from the photospheric region of the star, which is the first line. Then the circumstellar matter, which is what we call the focused wind. And finally, the atmospheric lines, which are intrinsic to the Earth, so we see them in every spectra. So in the other plots, I'm not going to show you the atmospheric length. I'm just going to focus on the stellar photospheric region and the circumstellar matter. And so the first thing that we see for the H alpha line is that the photospheric region has this kind of stereotypical P Cygni profile in which we have a blue shifted absorption here and a red shifted emission, which means that we have an outflowing wind, and part of it is being emitted because it's moving away from us on the other side, so it's emitting. That's this region. And it's also absorbing, coming toward us because we have a lot of clumping, and by propagating, it's absorbed to be able to propagate because we have a line-driven wind. And then we have the circumstellar matter, which can have the inverse kind of P Cygni profile that we have from the photospheric region, which means that when the wind is coming toward us, the circumstellar matter is moving away from us. And that means that because this wind is actually a little bit outside of the photospheric region of the star, it's the part which is being accreted by the black hole. So that kind of makes sense in a way that when we have the star, for example, in front of us, part of the wind will be going away from us because it will be going towards the black hole, which will be on the other side, for example. And then on the right, we have the helium-1 line, and this line is very interesting because we don't see it in the circumstellar matter, which means that it's not present in the outflowing focused wind region, but it really has a prominent absorption in the photospheric region of the star, which means that it forms in the inner regions of the region of the star. So we basically will use this line as a proxy for the motion of the star without the contamination of the focused wind. Now, the helium-2 line is kind of one of the most interesting ones. So on the left are the spectra in the LOHAR state, and on the right in the HISO state. So LOHAR state means low X-ray flux, and we are dominated by the quantized emission from the inner regions of the accretion disk. And on the right means high X-ray flux. And again, the top is the combined spectra and at different orbital phases. And the first line is the photospheric region, and circumstellar matter in the second region. And the first thing that we see is that the helium-2 line is present in both the photospheric region of the star and the circumstellar matter, also called the focus wind. But the photospheric region is shown with an absorption line, and in the circumstellar matter, it's with an emission line, meaning that the helium-2 line is actually emitting in the focus wind region, which means that the focus wind region might be denser and more constant peak than the photospheric region of the star, in which the line will be able to recombine and emit. And then on the right side, in the HISO state, we see the same pattern with an absorption in the photospheric region and an emission pattern in the circumstellar matter. But what changes here is the broadening of the lines and the emission of the lines, meaning that the line is actually more intense in the LOHAR state than in the HISO state, and is also broader in the LOHAR state than in the HISO state. And this is also the case for the H beta line in the both different states as well, except that we don't see it in the circumstellar matter component again, so it can be used as a proxy for the photospheric region of the star. And we have a blue shifted absorption, which is broader in the LOHAR state than in the HISO state. And we also have an additional red wing actually here in the LOHAR state that we don't see in the HISO state. And the particularity of these lines can also be shown with the radial velocity curves. So this is the radial velocity with respect to the orbital phase. And in green is the helium-1 radial velocity curve, which means that it's a proxy for the photospheric region of the star. And the orange line represents the helium-2 line, so a proxy for the focused wind region of the system. And what we see here is that when the radial velocity is positive, which that means that the star is moving away from us. And when the star is moving away from us, there is this kind of anti-orbital motion of the focused wind, which means that the focused wind is coming toward us. And there is a delay of approximately 0.2 in days, around like 1.5 days, which means that almost at 1 or 2/3 of between 1 and 2/3 of the orbital motion phase, we have a delay between the emission from the stellar wind coming toward us and the focused wind moving away from us. And this anti-phase motion have actually been observed in the past with X-ray and optical kind of correlation to see how much the X-rays and the optical are delayed with each other. But here we were able actually to separate it from the focus wind region and the photospheric region, which means that it's not only the accretion disk which is kind of moving with the black hole, but it's also the matter in between the star and the black hole, which is moving closer to the black hole and so moving more with the motion of the black hole rather than the star. So now if we look at the orbital parameters that we can extract from the disentangling method, so on the left is the low Earth state, high soft state on the right for the H alpha, helium-1 and helium-2 lines on the left and on the right. And the first, actually, we don't really care about the period strength, but what is interesting here is the semi-amplitude of the radial velocity, which is the K1 value here. And for example, if you focus on the table on the left, so in the low Earth state, so low X-ray flux, when we have the H alpha line in the low X-ray flux, we have a semi-amplitude around 95 kilometers per second. And if we compare with the high soft state, we have a higher value at 96 kilometers per second. For the helium-1 line, we have 88 in the lower state, 82 in the high soft state, and finally in the lower state for the helium-2 line, we have 87, and then high soft state 82, which means that on average, the velocity of the lines for H alpha, helium-1, and helium-2 is actually higher in the lower state than in the high soft state. Well, actually, kind of the H alpha line is kind of the exception because H alpha is not only in the photospheric region of the star or in the focused wind, it's kind of everywhere. So it's very hard to only isolate the H alpha line for one region. So that's why the helium-1 and helium-2 are good proxies to kind of probe the photospheric region of the star and the focused wind region. But on average, the velocity of the wind, so for the helium-1 line, is higher in the lower state than in the high soft state. And for the focused wind, is the same. And now if we look at the intensity of the lines with respect to the orbital phase, so which is like the strength factor with respect to the orbital phase on the left here and here on the right, the main difference here is that here we focus on the helium-1 line. So again, proxy of the photospheric region of the star. And on the right, we have a mix of helium-2 and H alpha. And when we see here on the helium-1 line is that the lines that don't really change in intensity with respect to the orbital phase, which kind of makes sense because the intensity of the lines for the helium-1 is really governed by the intrinsic structure of the star for the photospheric region. So from the inner layers, which doesn't change that much with the orbital phase or with the X-ray flux. But because the blue is the hard state and the purple is the soft state. But on the right, when we probe the helium-2 line and the H alpha lines, as I told you before, H alpha is kind of not a good proxy for viability because it's already very viable all over the system. But if we probe, for example, helium-2, which, if I remember, are the crossed line, we can see that it highly depends on the state, first of all. So the hard state usually have strength factor higher than for the soft state. And then it also depends on the orbital phase, meaning that there is this dotted curve, fitted curve here, which represents the best fit for the orbital motion of the helium-2 line emission with respect to the phase. And we see that, for example, at phase 0, the strength factor is higher than at phase 0.5, which means that when the star is in front of us in the line of sight, the strength factor of the helium-2 line is higher than when the star is on the other side. And that can be seen in the absorption and emission lines, because I told you before that helium-2 can be seen in emission in the focused wind, but in absorption in the photospheric region of the star. So basically we have a variation of the strength factor, so of the intensity of the lines in absorption and in emission of the helium-2 line and of the H-alpha line with respect to the orbital phase that we don't see in the helium-1 line. So now when we combine the optical and X-rays results that we observed, this is what we get. So this is the light curve for MAXI in the 2 to 60 eV energy range, so in X-rays, with respect to the MGD. And on the right axis here is the strength factor. So again, the intensity of the helium-1 in red, helium-2 in purple, and H-alpha in orange. Again, for the same MGD for the time of our observations. And what we see here, so the green regions are the soft state, and the purple or kind of pinkish regions are the hard state. And we can see that when we are in the hard state, the strength factors of the lines for the H-alpha helium-2 and helium-1 is way much higher than when we are in the soft state. But these results can also need to be taken with a pinch of salt, I would say, because we have a lot more coverage in the hard state than in the soft state. But still, what we observe, even with a very sparse coverage between the two states, is that on average, the soft state has a very low strength factor compared to the hard state. And also that when the X-ray flux starts to increase, for example, around here, as I mentioned before, we have a delay of response between the X-ray emission from the accretion disk and the optical emission from the star, which means that when the X-ray is irradiating the star, the response for the lines to be ionized and to have basically a quenched wind will not happen instantaneously. So it will have a little bit of delay. And this delay we can actually already see in the lines here because the flux in optical doesn't drop significantly below the value that was achieved during the hard state. It still needs to take some more time before really reaching the level it has in the soft state. So basically here what it shows that when the X-ray flux increases, the wind becomes more photoionized, and because the wind becomes more photoionized, there are more ions happening in the wind, and then the ions don't have enough bound electrons to actually propagate and absorb, which means that the wind density needs to decrease and the wind needs to slow down, which is also what we observed actually before with the lines and the semi-amplitude of the lines, where the wind is actually faster in the low hard state than in the high soft state, because the flux in the high soft state is so high that the ions don't have any more electrons and cannot propagate. So the main conclusions here are first that we have a very strong variability of the lines, which means that the lines have different origin in the system, and some of them can be used to probe the photospheric region, so the helium-1 line, and others can be used to probe the focus ring region, which is the helium-2 line, with the helium-2 line. Then the high ionized helium emission is shown in the circumstellar matter, which is interesting because it shows that despite the absorption showed in the photospheric region of the star with the helium-2 line, we have actually a denser material which is leaving the star and going towards the black hole, even though it's closer to the accretion disk and higher exposure to X-rays, it will still be dense enough to re-emit. Then the emission strongly depends on the wind density and the photoionization, which means that the denser the wind, the more absorption it will have, but also it depends on how much the X-ray will emit, because if the X-rays are very high, then the wind will be quenched and it will not propagate as fast as it would have if the X-rays were lower. And again, we have this X-ray optical anticorrelation, which means that the higher the X-ray flux, the lower the velocity of the wind and the lower the optical emission from the star, from the star and the stellar wind. Now, I would say the opening question that you have with these results is, now that we actually saw that there is a very strong anticorrelation between the emission from the accretion disk and the star, how does the stellar wind could actually impact the accretion rate variability in the disk? Because as I told you in the beginning, in the low hard state, we are dominated by the emission from the Comptonized region, and this Comptonized region is highly variable, so we don't see it in the soft state. But still now we don't really understand why. So we don't really know why these systems transition from a low hard state to a high soft state. But it seems that the amount of material that will be fueled toward the accretion disk, so basically the amount of wind that's going to be inside the accretion disk, is highly variable on how much this accretion disk is emitting in X-rays. And so if we are able to account for how much the stellar wind will be quenched during the high-soft state, we can then estimate how much it will impact the amount of matter fueled into the accretion disk, and then how much the black hole will then accrete in the soft state and in the low hard state. Because in general, the black hole is also accreting more in the high soft state than in the low hard state. So this can actually help us understand more the accretion rate variation in the accretion disk and how they can transition, how X-ray binaries in general can transition from a high soft state to a low hard state. Okay, so that's it for me, and I will be happy to answer your questions if you have any.
Thanks a lot, Brigitte. So the floor is open to the question.
Okay.
Is there anyone who wants to start?
Question. So you said when the flux is lower, the wind slows down, or when the flux is.
So yeah, so when the flux is lower, the wind accelerates. But when the flux is higher, then the wind is quenched and decelerates.
And do you know how that the total weight of mass that's ejected is kind of, you think that's the same and it just gets denser when it's slower, or you think the total mass loss rate is variable?
The total mass loss rate is actually quite similar, even though when the flux is higher, the star has a slightly lower mass loss rate. I think it's around like between 2.6 to in the low hard state to the 0.6 10 to minus 6 and around 2 in the soft state, 2 times 10 to minus 6. So the change is very, very small in the high soft state and the hard soft state and the lower state.
Okay.
Thanks.
Any additional question? If not, I do have one. It's kind of funny that you do see H alpha emission and then you got helium-2 emission, but you don't have any helium-1 emission. Is that something
Yes.
that you expected, or?
Actually, no, I was not expecting that. But it's also because usually when we probe the emission of helium, if you can go back to helium one, yeah, it's kind of a mix of the photospheric region and like whatever the wind region is. But because in the disentangling we can actually probe closer to the star and further away from the star, it kind of makes sense though that the helium-1 will kind of completely be destroyed if we get too close to the black hole because the X-ray flux is higher on average, and also because the helium-1 actually forms in the photospheric region of the star and doesn't really propagate as the helium-2 would be able to do in a way.
Okay. And I do have an additional one, which is just a practical one. Here you have examples where you see the atmospheric lines, but of course from one spectrum to another, it wouldn't be like the other ones who are just moving, but the profile is not expected to change. But for the atmospheric line, the strength is changing from one night to another or for 1 hour to another. Is that a problem for that disentangling method?
Actually, no.
Have you tried, for example, to clean first the atmospheric line and then try the disentangling?
Yes, exactly. Yes. So yeah, exactly. That's a good point. The atmospheric light do change between the different observations, and especially also between the different states that we took, because one was in 2022 when the other one was in 2023. So really in different years, we really have to take that into account. And actually, with the disentangling, it's quite easy to fine-tune the shape of the atmospheric lines that we expect, because we can also manually kind of enter the parameters of the atmosphere in a given night, in a way, by comparing with database from other sources that were observed in a similar night. So we can always compare with other sources that were observed and put it into the model so it can accurately model the atmospheric lines that we have in the spectra.
Brigitte?
Yes. Can you hear me?
Yeah.
Okay.
Anyone else?
If you're talking, I cannot hear you. I don't know if I'm the only one.
Peter, I can see you. Do you have a question?
No, not really. Maybe I also didn't follow enough. I mean, I basically knew about some of the ionization in this mechanism. Would we be able to sort of study a kind of feedback loop in here because of this? You sort of suppress the wind. When you have more when you have more radiation, X-ray radiation, you has this ever been looked at deeper? I mean, it's maybe a kind of naive question. I've never thought about what it would really be for Cygnus X-1. Yeah.
Yes. So the feedback actually would be very interesting to investigate, but I don't know any paper actually who talked about the feedback from Cygnus X-1, especially because this source is kind of tricky to analyze for feedback for multiple reasons. First, because it doesn't completely reaches the soft state, the X-ray flux variability is very high, even within the same state. So I would imagine that your feedback would already kind of be very prominent in the lower state already. So if you increase the flux in the high soft state, I don't think you would see that much of a difference because the flux is already very similar. Even but because Cygnus X-1 bursts has flares sometimes, so it's it's really hard to kind of isolate one region when the X-ray flux will be homogeneous enough for you to analyze the feedback in this region at this moment in the given X-ray flux. And I would say that because also the wind is very clumpy, because there are a lot of papers about the clumpiness of the wind, it's also very hard to separate um, the impact of the wind once the clumps have been sent and the absorption is dominating, especially in the lower state. So I would say that the feedback would not be homogeneous depending on the orbital phase we're looking at, because we also saw that when the star is in front of us and the black hole behind, the absorption is higher than vice versa. So I guess the feedback is a very good, the system might be a very good way to analyze it, but I would say that it would be a bit hard because there are so many parameters which are highly variable in time and in X-ray flux that it might be very hard to isolate.
Okay, thank you. So very sort of random flipper. Too many things happening.
Yes, exactly.
Okay.
But that would be very interesting to maybe kind of have a very stable state, I would say, or region where we could isolate the parameters and not being too much variable.
Okay, thank you.
Thanks a lot. Anyone has a question to ask? If not, let's Brigitte again. And well, we should have normally another seminar on X-ray binaries next month, and then we have the last one on the active V star in May. In the meantime, I suppose you have seen that there will be a a small meeting here in Liège. So you're all welcome, of course, to propose things about BE X-ray binaries. We'll look at BE under various angles, and any angles would certainly bring something to the knowledge of those stars. So feel welcome to submit abstract. You have until March 15. And until then, well, see you next time. Thanks again, Brigitte.
Thank you. Thank you for having me.
And bye-bye. Have a good, I suppose for most of you, it will be end of afternoon. Bye-bye.
Bye bye.